The Milky Way, general. The Milky Way, Via Lactea in Latin, was named after its appearance as a patchy faint band of light from concentrated stars. It has two small satellite galaxies, the Small and Large Magellanic Clouds, SMC and LMC. It can be seen well far away from sources of light pollution, and with optical aid individual stars can be seen. As we are relatively near the edge of the Milky Way, we look into the plane of it, with the most stars. If we looked down on it, it would look like a giant disc-shaped Catherine wheel, rotating round a central bulge like the Andromeda Galaxy. Structure of the Milky Way. The structure of our galaxy has three main components. The disk, diameter 30 kpc, thickness 1 to 2 kpc, contains young stars, gas, dust, and locations of star formation in the four spiral arms. Our solar system is in one such arm, 10 kpc from the nucleus. The bulge surrounding the nucleus. Astronomers now think there is a massive black hole at the centre, and a halo, containing mainly globular clusters which are dense groups of quite old stars in a spherical distribution around the galactic centre. The Milky Way's spiral arms. As well as stars, the spiral arms in the Milky Way also contain large clouds of gas and dust, which are opaque to visible light. These clouds mean astronomers can't map the spiral arms. However, they contain hydrogen atoms, which are made of an electron spinning around the nucleus, a proton. When the electron reverses its spin, it emits electromagnetic radiation, frequency on 1420 MHz, in the microwave or radio region of the spectrum. This electromagnetic radiation does penetrate the dust and Earth's atmosphere, so this can be detected by radio telescopes, which are tuned to the same frequency. As our galaxy rotates, the radio wavelengths become Doppler shifted. Radio astronomers use the wavelength changes to work out the relative velocities of the gas in the spiral arms. They can then determine how various parts of the galaxy rotate. Classifying galaxies. The most used way of classifying galaxies was suggested by Edwin Hubble in the 1920s, where they are sorted according to their appearance from Earth. Spiral, S. Flattened disc-shaped systems like the Andromeda Galaxy. Barred spiral, SB. Similar, but with a bright bar running through the nucleus, from which the spiral arms emerge. Elliptical, E. Relatively smooth spheroidal distributions of stars, showing a gradual decrease in brightness from the centre outwards. Irregular, IRR. Very little structure or symmetry. Hubble's classification scheme. S, SB, and E galaxies can be classified further by assigning them a number or letter. Spiral and barred galaxies are given the letters A, B, or C, depending on the strength of the nuclear bulge and openness of the spiral arms, as A galaxies have a predominant nucleus and tightly wound arms. Elliptical galaxies are assigned numbers 0 to 7, depending on their shape. E0 is the most circular, E7 is very elongated. It now includes SO, which represents lenticular galaxies, a class between elliptical and spiral. The local group. Galaxies are grouped, and ours is a member of the local group, made of around 50 galaxies around 3 MPC across. The local group also includes the Andromeda Galaxy, M31, the largest in the group, the LMC and SMC, two irregular companion galaxies to ours, the Triangulum Galaxy, M33, which is a spiral galaxy, and several satellite and dwarf galaxies, like Pisces and Aquarius Dwarf. Clusters and superclusters. On an even larger scale to galactic groups, galaxies are found in gravitational agglomerations called clusters, which mostly have an elliptical galaxy in their centre. The nearest large group of galaxies is the Virgo cluster, containing about 2,000 galaxies. Its centre is 15 to 20 MPC away. Others include the Fornax cluster and Coma cluster. The latter is dominated by two very large elliptical galaxies and contains about 1,000 galaxies. It's around 100 MPC away. On an even larger scale, clusters collect in superclusters, held together by gravity. Our local group and the clusters listed above are part of the Virgo supercluster. Galaxies. Active galaxies. Most galaxies are made of gas and stars. They shine by emitting starlight. However, some other galaxies emit large amounts of energy, not in the same wavelengths as visible light, particularly in the X-ray and radio regions of the spectrum. These are called active galaxies and are the most powerful energy sources known in the universe. Their energy source is thought to be a very small nucleus, so they are also known as active galactic nuclei, AGNs. There are 4 types of active galaxy. Radio galaxies. These were discovered in the 1950s. These mainly elliptical galaxies are such intense sources of radio waves that they emit more than 1 million times more energy at radio wavelengths than normal galaxies. The radio emission often originates from symmetrical pairs of lobes that lie on opposite sides of the galaxy. Seyfert galaxies, discovered by American astrophysicist Carl Seyfert in 1943, these spiral galaxies have extremely compact but bright nuclei, strong emission lines in their spectra, and show strong and often variable emission of radiation at IR and X-ray wavelengths. Quasars, quasi-stellar radio source or quasi-stellar objects. Discovered by radio astronomers in 1963, their compact appearance makes them look like stars, but they emit huge quantities of energy in all regions of the spectrum, from X-rays to radio waves. Their high redshifts reveal that quasars are some of the most distant objects in the universe. Blazars. Discovered in the 1970s, these also appear star-like, but lie much closer than quasars, emit strongly in all regions of the spectrum, from radio to gamma rays, and can vary dramatically in optical brightness on a timescale of 1 or 2 days. AGNs. All AGNs, active galactic nuclei, are variations on the same theme, and the observed differences are due to the angle that they are observed from Earth and the mass of the black hole. To discover the nature of AGNs, it has required observations by astronomers from all over the EM spectrum. They agree AGNs are powered by matter falling onto a supermassive black hole that lies at the centre of the galaxy. This kind of collaboration led to the discovery of quasars. In the 1950s, strong radio sources had been matched with stars, but it was not until 1962 that the radio source 3C273 had its position determined precisely by radio astronomers in Cyril Hazard and John Bolton at the Parkes Radio Observatory in Australia. The exact location allowed Martin Schmidt to obtain its spectrum. He noticed strange emission lines that he realized were redshifted lines of hydrogen. Then he calculated the corresponding recession velocity as 47,000 kilometers per second. The Doppler effect. When stars and galaxies move away from us, the light from them is shifted to the red end of the spectrum. This is because the wavelengths are getting longer, and red light has the longer wavelengths of the visible spectrum. This is how we can tell the universe is expanding. The opposite occurs when they move towards us. The light is shifted to the blue end of the spectrum. This only occurs with galaxies in a local group, due to gravity. By looking at how much it is shifted, we can calculate their radial velocity. Calculating radial velocity. Lambda minus lambda O over lambda O equals V over C, where lambda equals the observed galaxy wavelength, lambda O is the rest wavelength of the galaxy, V is the velocity of the galaxy, and C is the speed of light, 300,000 kilometers per second. The value of these wavelengths is measured in angstroms. A. Hubble's constant. V equals capital H, lowercase d. V equals velocity, H equals Hubble constant, and d equals distance. Hubble's law. The Hubble constant is a value which tells us how quickly a galaxy will be moving away from us in relation to its distance from us. Scientists disagree on an accurate measurement of the constant. Most cosmologists agree on 77 kilometers per second per MPC. If the number is too high, we find stars older than the universe. The constant therefore supports the Big Bang theory. Cosmic microwave background radiation. CMB is the furthest and oldest signal detected by a telescope. Its temperature is 2.7 Kelvin. It is the heat remnant of the Big Bang, the background temperature of the universe. It is therefore evidence for both the Big Bang and the expansion of the universe. It is exactly the right temperature for the remnant of the Big Bang at this point in time. Its ripples are how galaxies are formed. They're not really ripples, but actually patches which are slightly hotter than the rest. The composition of the cosmos. Stars, etc., 0.4%, intergalactic gas, 3.6%, dark matter, 22%, and dark energy, 74%. Dark matter and energy. Scientists have measured the mass of galaxies by studying the light coming from them and their velocity. They always find that they are moving faster than they ought to for their mass. Scientists believe that there is some invisible matter, dark matter, which cannot be directly observed. Dark energy works differently. It appears to be a force which moves galaxies away from each other. The expansion of the universe since the Big Bang should have slowed down the rate of movement between galaxies. The opposite is happening, however. The rate of movement is increasing. Scientists believe an invisible force, dark energy, is responsible for this.